Welcome to the discussional part of the Arp Evidence series. In this episode, we will be discussing the quantization of redshift and looking at Jim's concept of whether we can use plasma redshift to explain what we see in terms of ejected material and in terms of the quantization of redshift. Now, I warn you, this is a long episode, but I felt it very important to leave a lot of the discussional parts in there. I may well produce a shorter version of this in the near future. Now, before we start, I'd just like to say a massive thank you to all of my Patreon supporters and those that support me via PayPal. If you're interested, the details for that are down in the description. But for now, enjoy the conversation between me and Jim discussing the quantization of redshift and plasma redshift. Okay, so in my mind, let's start with the whole concept of plasma redshift and the thing that you mentioned a while ago, which was the whole idea around, and I believe it was a discussion in one of the Thunderbolts forums that you kind of pointed me towards. But there was this whole concept of, one of the reasons people dismiss the whole idea of quasars being much closer than they are is because of this alpha Lyman forest. Is that correct?
Right. We see the hydrogen that's leading up to it. We see a continuous range of redshifts. It's not just all like the high redshift at the quasar end, and then they see varying degrees of redshift right up to it.
So just for people, what does the alpha Lyman line indicate?
Oh, that's the absorption from the hydrogen.
I don't know whether this is the best image to look at, but effectively, wow, they're all really small. But normally when you look at objects, you have different lines that are being removed, and so when we look at quasars, there are particular, I guess you'd call them signature lines that indicate that it comes from the quasar. But equally, there are if there is material that sits, if there's material that sits, so if this is the quasar that is emitting light, then there is a spectra that it produces based on its type, like stars produce a particular type of emission, and that gets shifted. So if that produced a series of lines, then, and this was, let's say, one end of the spectrum, the other, then when we receive it and it's redshifted, then what would happen is it would end up being shifted more towards one side. Yeah, so that's the basic concept of the redshift. But the Lyman alpha, or the concept here is that there are other objects in between. If we're here, that's as the observer, then these clouds will also produce a spectra, and they will be shifted as well. And what we're seeing is that shift, that additional spectra in between it, is shift different amounts. Is that correct?
Right.
So therefore you have like a fingerprint which sort of identifies that maybe this was only shifted a small amount and this one might have been shifted more. I should draw them as different fingerprints because it's not the same print as here. But effectively, it creates that myriad that you see here, which is a whole mixture of different things, and you have to try and work backwards as to what might happen. So why is it that is used as an excuse to say that the quasars must be very distant? Why is that the mainstream reasoning for that?
See, if you want to argue like Arp did that it's intrinsic redshift right at the quasar, then we shouldn't have any hydrogen in between us and that with varying degrees of red. It should just be a high redshift quasar, and then all this local, pretty much non-redshifted hydrogen in between. But the fact that they see it going all the way up, that actually is an argument for the plasma redshift idea. You would just have an electron, if it's caused by electron density, you would have that electron density falling off from the quasar. So it wouldn't just be the quasar itself, but the area around it would still be redshifted too.
Yeah. So this would produce a cloud of material around which there'd be some sort of ionization, which would fall off. So this whole area produces a shift in the plasma.
Right. And then you wouldn't see quite as much at the end, but they don't. And what they view it as because there was a higher degree of ionization back and less neutral hydrogen back in the early universe, back where they think the quasar, what they're seeing. So that's how they explain the various degrees of hydrogen they see along the way. But really what it would be in the plasma redshift idea is only a little bit of that hydrogen would be out at redshifts going up to the quasar redshift, because the redshift would fall off quickly away from that front.
So, and I think we need to take a step back here, because the problem is that you have a quasar. When we observe the majority of quasars, they don't have just a single redshift. They have many different additional lines that indicate that there were a variety of different hydrogen absorption lines in between us and it. That's correct, right?
Right.
And therefore that is used to explain, because the ones, I guess there's a redshift difference between, let's say, the first cloud and where it is, and they use that to explain, well, in this part of the universe, because if this is like 5 billion years old or more, then at that age of the universe there wasn't much hydrogen cloud, and therefore you wouldn't see much absorption, and that's why we see the shifts that we do see are later on.
Right. Yeah.
But if we were to did Arp ever have an explanation for that?
Well, see, he wasn't thinking of the plasma redshift idea, although his so many correlations that he came up with, I mean, just observationally, would have made more sense to him right away if he was familiar with the plasma redshift idea. I think he would have jumped right to that conclusion. So many patterns, like the one he found with the brightness changes going with decrease. Increase in brightness was a decrease in redshift.
Yeah.
But that makes perfect sense. If recombination is what's giving off all the light, then that obviously means fewer free electrons for the redshift. So you'd see an obvious correlation in the plasma redshift. As the free electrons recombine, you get the light, but then less plasma redshift. And then that would make sense of his arcs too around when you see a lower redshift object at the center and then these shells or arcs that are higher redshift, that also makes sense because you would be looking through, if there is a shell of electrons, an ionization front. Even the mainstream knows that these shock fronts are ionization fronts. So if you're looking more edge-on through those, if you're looking right to the object in the center of a shell like that, you're looking through the thinnest part of the electrons then. Whereas if you're looking kind of edge-on it,
from that direction, let's say, which
yeah, if you're looking right into the center, you'd see right through this shell of electrons with only a little bit of redshift then. But if you're looking at the edge of the shell, then you're looking through the most free electrons then. It's kind of like how the plasma stickman figured how you get that shape when you're looking at the
sort of like that with like that.
Right, it's where you're looking through the most material that it looks, you get that. That shape.
So again, here we're the idea is you have these expanding shells that sort of form, I guess, in some sense, sort of like a torus that goes around it. And obviously, there are certain parts you can look where you would be seeing less of it, and if we look in this direction, you've got all of this, and then all of that underneath it.
Yeah, well, even if it's just a perfectly spherical shell, you're still looking through the most at when you look right
to the center.
When you look towards tangent to the surface of that shell, if there's an electron shell, when you look. almost at the surface of it.
Yeah, along that line there, like that.
Right. You're going to get, then you're going to see through the most free electrons, if there are free electrons. And again, the mainstream knows that there's shock fronts out there. So that would explain why you see those rings and arcs then.
But how does that help us explain the Lyman alpha lines? If we go back to that whole idea of why we see Lyman alpha using the concept of plasma redshift.
Well, yeah, just that the object themselves aren't, like in Arp's idea, the idea is that this new matter, like those quasars, so only that should be redshifted and the surrounding material. But if you have electrons out in these shells, then you're going to see all the matter out inside of that is going to be redshifted to a lesser degree.
Yeah, so it would produce, like, I don't know whether it would be a bell curve, but there would be, if that's the center of the object, that's where you see the highest redshift, and then it would sort of fall off as you move outward from these shells. Yeah,
because the electron density is going to fall off out even past the shell, past the as you move out from the electrons. Basically, it's not like a solid, not really a solid shell. It's
no, it'd be actually, I know what you're saying. It's a gradual change as you move here, lower and lower. So this would be like a curve, sort of idea. But I don't understand how does that explain the fact that you end up with these additional lines, or are we suggesting that there is actually material that is doing that in between this, as well as the fact?
Yeah, there is going to be material between us and that, but a lot more of it is going to be at lower redshifts, which is what they see, and they explain it as just that there wasn't as much neutral hydrogen back at.
Yeah, so this would be the high redshift quasar. So you'd have electron density that sort of would reduce as you go further out. So it would produce, I guess, in some sense, depending on which angle you looked at, there would be a smearing of the redshift, lower redshift as you go further out, and then these clouds here would be much lower excitation. So they would produce a small amount of redshift, and then maybe here it would be even less. So there would be additional, and obviously they have absorption lines for the hydrogen cloud, so they would appear in a slightly, if that was where they normally appeared, now they appeared in a slightly shifted position, and for these it would maybe shifted even less, whereas here it's shifted much more. Yeah?
Yeah.
So when you add all of that up, you end up with a pattern that matches what we see here. So it's an alternative way of explaining the Lyman alpha lines without having to have the quasars at a massive distance in order to have this gap here that they need in order to explain why these are shifted less than the quasar itself.
Right, and see, that's what didn't work with his like waves of, if you want to attribute it to age, and then you'd have these waves of creation that wouldn't explain the lesser redshifts. Then that you would have these high redshift, and it's hard in his theory to explain both the quantized redshifts and also that continuous spectrum of redshifts that you get from the Lyman alpha.
Right.
So that's the question. But what's I think most important is, as he shows that the quasar redshifts are quantized, but not all these other redshifts of, for example, these shells and arcs. Those are higher redshift than the object that appears at the center of it. But he's not saying that those are quantized. And so that's we have to keep in mind, is you want to explain how the quantization can't be intrinsic to the redshift itself. It has to be something that's happening at the quasars, not in these other plasma redshift, where we get lower degrees of plasma redshift. So the way I would explain that is that it's the shock fronts themselves that are doing really the quantization, because of what you should have in shock fronts is waves of ionization or waves of recombination, when it not just a gradual collapse. Like as a shock front moves out and slows down, you have an electric field, you have the electrons driven out. This just, even according to mainstream theory, you have the electrons driven out ahead of the protons. But once that shock front slows, you'll get recombination all, pretty much all at once, all in a very short period of time. It's not like this gradual. In other words, you could see how you'd get quantization of redshifts from that, just from, since the universe is mostly, a lot of hydrogen and helium out there, that's when that recombines, you'd lose all at once all those free electrons.
Hold on. So you would have the quasar at the center, and then you have.
Well, the quasars are out in the. You have a galaxy at the center, a lower redshift galaxy, and out at those jets, you'd be seeing out into these shock fronts where the mainstream knows that there's free electrons at the head of them, so we'd have to be seeing the quasar through those shock fronts.
So we have a galaxy. This is my beautiful drawing of a galaxy, and then somewhere further away we see a galaxy that sits across from a line, or across from a line from that. And so in terms of what ARP sort of found is that these were at very specific values, and they went, so this would be higher redshift and this would be lower and lower, unless of course these then spawn new ones, but let's for now not worry about that. So there were specific values, and I think it's off the top of my head 0.3, no, 0.061, 0.3, 0.6, 0.96, and then 1.41 and 1.96, something like that. But there were generally, when you looked at the distribution of redshifts was really, not always exactly, but very close to these values, and they tended to group. And you saw that across, it wasn't just quasars, but galaxies as well. But again, that's, if we look at the idea in terms of the plasma redshift, then these objects, from what you're saying, is where would the shock front? We're talking about the shock front around here, or from the fact that there's material ejected along here that's then impacting along this line?
Right. Well, where you see the quasars are the bright object where there's all this, obviously if that light is coming from recombination, then that's really the collapse of one.
Right. So you're talking about like this is what you're sort of saying, is that there are particular shells, so the material is being moved outwards, and the reason that you find them at this value is that corresponds to, in fact, actually these are the wrong way around, because you'd have higher redshift, not lower redshift. So this would be like the highest, one of the highest, 1.96 or something like that. And that would be 1.41. And that's because here you would have, are you seeing it that it would be particular, like hydrogen, helium, that would be recombining at this point? And then there would be other material at that point. Did you see that as a step change in terms of the material, or just in terms of that shock front from this galaxy moving outwards, and then it reaches a certain energy level? Because it wouldn't have to be distance, would it? This distance is not the relevant thing. The relevant thing is the electron density and whether it slows down enough that recombination takes place.
Right.
But would you see that that it would be predominantly different materials that would cause that recombination at different points, or is it just more to do with, why would there be surges at different? Because this would be ejecting material all the time, but obviously it slows down, right? So at some point, some of the newer material catches up, and you have a recombination event. And then maybe this is sort of in line with something else, which is why you then end up with that being a focal point. But that continues onwards. That's the idea, though, isn't it? That would continue onwards.
That's what I want to look again at his. He shows observations that show a jet, as he interpreted too, possibly jets going out and hitting these arcs, and then that's where you would get the right angle jets. But that's what we should have if there are charged layers, and then you have a discharge to that. It would spread out in the.
I mean, this maybe doesn't show it quite as well, but this does show this idea of these shells. So this image here goes with this one here. So it's ARP 215. And again, you can see here that the shells, it's much more obvious in this other image. There are jets coming out of the galaxy. But the one he often refers to is, well, I mean, this is the one where he shows the shells coming out of NGC 7252, which I have an image of 7252. It's, where did I put it? 7252. Again, weird. When you look at these in two different images, 7252 and this one's 7252, look very different. But if you look in this one, again, clear jets coming out of it. And again, very clear shells in my mind, these shells. And that the colored image that you see, this one here, is of that same galaxy. But then you can see the shells of material. And that's, just gases that are being ejected, but they do show this concept of the shells. I think the famous one in terms of the jet is, and that for me is always the one I looked at, and it's such an obvious shell or boundary that it's hitting, and the fact that you see this one here as well, that to me that comes back to that idea you're talking about shells, but then.
And if you just keep in mind that there should be, and if those are shock fronts, there should be that charge separation there. That's almost like a double layer, except usually you think a double layer is more static, but it's effectively like an expanding double layer. But
right, so this would be moving out along with the material,
right,
and then you would have certain objects that are. And whether they're being formed or whether they're being energized, for now I guess that's not the important point, but let's say that there is a quasar that sits along one of these lines, maybe further out, then this shock front, expanding double layer, would continue to move outwards. But then I guess the question is, in terms of what we're talking about here, if that's that boundary going outwards, I mean, the fact that we see this in this image here, I'm just trying to think of it in my head in terms of how we would explain the quantization, and then still link it to a quasar, because why wouldn't you see? And I guess that comes back to maybe the arcs, which are just redshifted. Why don't we see just arcs that are redshifted? And I've sort of answered my own question, because we do, and we call them gravitational lenses.
Right. Yeah. Exactly. That's what is showing up as gravitational lensing is these, and the reason they think it's more distant object being lensed is because of that higher redshift of the shells than whatever's at the center. So
thinking about this, so this quasar would sit here, and the reason that we would see it as a 1.96 quasar is then more to do with this shell. So the fact that you've got a higher electron density in this expanding shell that it may be traveling with. It may be part of that shell, and maybe the majority of that shell is actually concentrated in a much narrower beam in terms of the quasar. But then, in my mind, and I guess the question still is, does it travel? Does it move? Because obviously we don't necessarily see this, but Arp's view was very much that these would continue outwards. But my question would be, is if we were to observe this over a long enough period of time, why would that mean that it's a distinct value and not a range of values between here and the next one? Like, would it switch off and then switch back on, or would it stay at 1.96 and then slowly sort of move down, and then it would sort of continue along a line and then just sort of collapse down to the next one? I'm just trying to work this out. Like, how would these shockwaves create what we see as the concentration of redshifts around here?
Yeah, I'm gonna have to look at the numbers again and see what the. Are you right? Are you using those from the book? The point.
Yeah, I've got the book. I think those are. And then the other interesting, I guess, side note to all of that is that he also sort of discovered that there was a step change. You know, when he compared, I think when he was looking at the radio quasars, and he looked in two different sections of the sky. One would be the more local, and one would be more sort of associated with the Virgo supercluster. He saw that there was a difference. It was only a 3% difference, but there was a 3% difference in the 0 point, the offset for the redshift, and he speculated that meant that objects that were, you know, potentially further away, so on a distance scale, that the values that we would see here would be shifted more. So you'd end up, the further objects are away, they would be shifted. You know, he didn't really speculate as to what that jump would be over a specific distance, but he used that as one of the reasons to explain why, when you examine the whole catalogue of quasars, that actually this excuse me, the quantization disappears, it smears out. And his argument was that was because when we look at very specific small sections, so look at the Virgo cluster, look at our local cluster, we see that quantization very strongly. But obviously, if objects are further away, let's say that there are other quasars here, then this tends to smear out all of it. And again, in terms of thinking about this concept, in terms of the shells, can we explain that as well? Admittedly, it was only like one. I've only seen him talk about that once. It's not like there is a huge catalogue of data to support that 3% increment over distance. Yes, 0.061, 0.3, 0.6, 0.91, 1.41, and then 1.96, and that's the values that that's using that the equation that what's the chappie's name, Carlson, he came up with, the 1 plus Z2 divided by 1 plus Z1 equals 1.23. And then if you look at the values that he finds in his quasars, they obviously match those numbers very closely, but not always. Like in the one that he's got just above here, then his 0.96 value, or the 0.91 value, is actually 0.96. But generally speaking, the peaks occur very close to those values. Yeah, and then he sees the 3% difference when he's looking at the 12-hour radio quasars compared to the 0-hour radio quasars. And his view was that one of them was, so that the 0-hour was local, therefore we didn't see a step change, and the 12-hour ones were part of the supercluster, therefore further away, and therefore they had a different starting point. So they start, rather than at 0.3, they start at 0.34, and then everything is shifted by 3%. So it still follows the same pattern, just 3% higher. Because if we think about in terms of the plasma redshift, then these would be shells. So this would have a higher electron density. This would be a lower electron density, and this one even lower. That's the concept, right? As you move further out, but these shells themselves would be expanding outwards,
Right.
and therefore, as this continually pumps out more material and these slow down, wouldn't you also therefore expect them to get closer? So in effect, the spacing would get larger if this is decelerating,
Right.
which we sort of do see in terms of the positioning of them, and therefore there has to be a critical point at which, because it's in the front we're talking about, isn't it? So effectively, although you might have electrons here, really what we're seeing is them building up at the edge of this. That's the idea, right? These almost act like a sort of shield is maybe the wrong word, but the material that's kind of being pushed outwards, the electrons are sort of, if this is a double layer, sort of being caught up in that. So therefore you would have higher electron density right at this edge. And therefore there would be a very small band within which you would see that redshift. And then again, a small band within there. And then in between here and here, you might see some, but it's significantly less than at this point. That's the concept, right? That's how you would get to quantization, because it would be these shock fronts that are moving, relatively speaking, quite slow, that would cause that. Am I correct in thinking that?
Right. Yeah.
Which sort of matches this idea of when we look at these images of these shells that we see in the variety of different ones, and the fact that we see shells expanding from some of these, and I mean, this is a beautiful example that you have these shells that move outwards from the galaxies, and it would only be at these edge points, objects that sit within that edge point, that would see that. Now, the question, obviously, that then springs to mind is, okay, if that's the case, then why do we not see material when we look at quasars? Why do we not see an arc as well as the quasar?
Well, some of them we do, like the images of quasars do show a little bit of, like, they don't really show the whole a whole shell, but it looks like a curved front on the.
There are some classic ones that these are a little bit extreme, I think, but these are the classic ones that they use to explain the Einstein cross concept, and here as well. So where you do see material that sort of connects them together. And I guess, to be fair as well, we don't really image that many of them. A lot of the quasars, are you see them as a dot, and some of them, like these are deep field images, so not necessarily the ones that are the closest to us. If we take, this is NGC 3067, where there's a stream of material coming out, and there's a quasar that sits right here. And again, if we look, it's not as easy to see. That's the quasar, and that's the galaxy. So I guess some of it also sort of depends on, like, why do we see objects? And that's because obviously there's excitation of the object, and obviously a quasar, depending on what you think a quasar actually is, but we know that it does output a significant amount of EM waves, not just light, but ultraviolet, radio, depending on the frequencies it's active in. And that sort of means that when we look at this concept, that even if there was material here, then that doesn't necessarily mean that the material is visible to us.
Right.
And I also wonder whether the quasar itself, because again, you look at some of these, and the material that gets ejected doesn't necessarily always have to be in these large arcs. Sometimes even when you look at the ejected material in that image that we looked at before, I'm pressing all sorts of buttons now, it doesn't always part... no, not that one, part 4. Here, so sometimes it's narrower and sometimes it's further apart, and it gets thinner as it goes further out. And it could well be that within here there's a very narrow band within which it ejects material out of whatever the core is in the galaxy, and that is, as it moves sort of further out, that shock front would thin and sort of spread further out, which is why you get the arcs. And maybe it is that the quasars themselves sit and actually sort of pull some of that material in towards them. Whatever you believe that they are, whether it's a plasmoid, then that's still going to require material to form it. And when it does form, the question is, does it then consume some of that material that sits around it, and therefore would you end up with very little material when you do form a quasar? And when you don't, then you do see larger arcs. I don't know, that's sort of speculation.
Right, yeah, it could like a discharge to that shell, and then it picking up material in that shell.
I mean, something has to cause... I mean, it depends on where the process starts, whether it starts... the quasar is formed right at the beginning, or whether it's material that moves out and that some event causes it to compress enough to form something else, and whether we liken that to, is it like a star, or is it like a plasmoid? Whatever it is, the question is, does it form here, or does it form at these shock fronts, or during its journey out, and then it meets the shock front, and yeah. I mean, like you said, the discharge, if we think of this in terms of, taking one step back, in terms of bubbles, as it meets this boundary, is there some condition that causes, something else to form? Because again, we're talking about double layers here. I think the other thing to pull into this discussion as well is that paper that you found on galaxies. It wasn't necessarily quasars, but it's early galaxies and electron density, and the fact that they'd surveyed, I forget how many it was. It was top of my head 90 or 190 what they considered to be older galaxies, and then the whole catalogue of our more local galaxies, and they'd compared the redshift of the two groups, and then also the electron density of the groups, and they saw a clear link with objects that had a higher redshift also had a higher electron density. Now, obviously, their conclusion was that was because these are younger galaxies that have more active star formation, which produce more ionization, and therefore that explains the higher electron density, and not really linking the idea that actually the electron density could be why they have a higher redshift.
Right. Yeah. Right. That's what gave me the idea that was the right track, is using the electrons to explain the plasma redshift idea. And the other thing too that struck me was, and I still have to go through more quasar pairs, because if I find even one that would shoot this down, would be to have a... Well, one thing you notice when you look at all Arp's examples is that I noticed a lot of these quasars were seemingly ejected like across the sky. Some more towards us and some away, but not. We should stumble on one that's ejected almost exactly towards or away from. And I wasn't seeing that, which also gave me confirmation that maybe this idea of looking through these shells is what's doing it. Because technically, if this idea is right, then if we have a quasar ejected exactly towards us, then it shouldn't have much. We shouldn't be seeing too much more redshift than for the galaxy. So the fact that we're not seeing that, again, if I even stumble on one where it looks like one is ejected almost exactly towards us and one away, then that would kind of shoot down that.
But you wouldn't be able to see it though, because if this is the host galaxy and one comes towards us, I suppose it depends on the sort of the distance.
Yeah, if it's not
one would be like right on top of it, and you could argue that he does indeed show. He does have galaxies that have quasars that sit in the arms. Very much in the arm. So could that be an example? But then you wouldn't see the one that sits behind it. Do you know what I'm saying? I'm sure where was a good example of one that sits directly in the arm. That's his classic. Well, there's this one. I suppose you could argue whether or not that connects in the arm. So this is Markarian 205 and then GC 4319, which sits up here, sort of connecting through that filament. You could argue that might be more towards us, but then you would argue that there's enough separation that you should see it behind on the other side. But again, and I think there are other examples where they sit very much in the arm of the galaxy. And then there are also the examples of like this one, which is it's not necessarily, they're not necessarily quasars, but there's certainly we see active radio objects being emitted along the axis, sort of the spiral arm structure. And then there's another one as well that shows that. So it depends on how you look at the data. The problem is that it's separating out. Yeah, this one. Again, they're not. These two are not quasars. They are. I think these are radio sources. Yeah. And they may well. And again, see that? See that? Shock front again. And then this one, this is another interesting one where you have these blobs along the arm. And I'm not sure whether it's one of those. I'm not sure in this image whether any of these are quasars. I'd have to go back and have a look. But yeah, I know what you're saying in terms of you see, I would argue that you wouldn't see, if it's directly towards us, that you wouldn't see the other pair. So therefore, you would only ever have one.
Yeah, that's if it was exactly towards you. That would be a very low probability of seeing one exactly that way. But if you saw them more or less along your line of sight, where you'd still see them as a close pair.
The question, right, and going back to, because I think it's still worth exploring, is if there is indeed a galaxy, and if you are correct, and it travels out directly towards us, and that means that when we look at it, we're no longer looking along the edge of the shell, we're just basically looking through it, that the object itself would no longer be, let's choose a different color, but it would not be as redshifted. It would just be, that's a really bad color to choose. It would effectively be very close to the parent galaxy in that case.
Right.
And therefore, would we just say it's a dwarf galaxy? What would it look like? Is part of the reason that we see these as highly energetic because of the combination of what's going on in this double layer and the fact that no, in fact, that's not true, because you'd still have the expanding shell here.
Yeah, actually, yeah, you're right. We could remember the reason they think the quasars are so bright is because they are
so distant.
But if we use the if we put them at the same distance as the galaxy, it would be interesting to compare then the actual brightness and then see if we're looking at this, what that would compare to, just that brightness of.
Well, the question would be, because in essence, does that not create a hole in this argument for plasma redshift? Because if the difference is that, depending on how you look at it, so if you're seeing it through the edge of this shell, therefore creates a greater redshift because there's more material that you're seeing it through to cause that shift, versus if you look directly at it, then you should see a difference in. You shouldn't see this quantization as direct, because if your angle changes, so depending on how you look at it, then surely that would cause a difference to the value of redshift. You see what I'm saying?
Right.
If we look directly at objects,
we shouldn't. Right, we shouldn't see any. If there's anything ejected towards us, we shouldn't see any more plasma redshift at all than for the.
Well, you'd see some, surely. But it would be small in comparison to. There'd be some. There'd have to be some, because there's still, electrons in between in that shell. But you would only be. It's only the distance traveling through this section compared to the cross section. If the majority is in this, that's a really bad curve. If the majority is in the edge, then the maximum you'd see is there, because you're cutting through this whole line, compared to here where it's a really small amount. So it might be too small to measure, but in theory there should be some. But again, how you measure how much would be in this, I guess it's open to debate. But that would mean, because even angles that are different to that would create, only these perfect angles that allow you to go through, slice that plane at its maximum, and for shells that are large enough, you would see the biggest redshift. So wouldn't you see? So all the ones that would be down this line would adhere, and let's say that's for this one that we're looking at is 1.96. Let's say if you look down this line, but that means that when you look through this way, it would be almost nothing. So maybe 0.00. I'm not even going to give it this number, because I don't think it necessarily would be that number. There would be something, and maybe it's not measurable. So maybe you would discount it from your data anyway, because you would not see it as redshifted. But the question is, if you graze the angle like this, would that change the value of this significantly, that it no longer forms that, clear pattern that he saw, where he saw the values going up, peaking around? They were not all exactly the same. Do you see what I'm saying?
Right. That's why I do want to find any examples of, if there are any examples of quasar pairs that actually the first step would be to look for the maximum or the minimum angle between us and the ejected pair.
Yeah, so based on I guess you could look at the distance between those two that are ejected to try and assuming that they are similar redshifts, to try and work out what angle we're looking at this at, whether it is sort of more towards us and away from us versus directly side to side.
Right, and that basically you're looking for the biggest difference in redshift, because there still is the actual Doppler redshift. There should be of it, so you should.
Yeah, and he goes through many examples where he shows that the difference between one and the other shows the ejection velocity, which again, you can't fault the logic that does indeed show that these objects are indeed moving and being ejected, and that speed slows down as you move further out, which does still fit in with this idea, but I'm just trying to picture it in my head in terms of yeah, it would, because all of these that move out to the side, we would still be seeing the majority of it through, this sort of maximum angle. And maybe that is why we don't see very many that are, if this is directly towards us and that is directly away from us, because the redshifts, this one would have a redshift which would be almost unnoticeable in that case. But if that is true, and you would have to argue that there must be galaxies that eject material directly towards us.
Right, but then we wouldn't be seeing it as a high redshifted quasar. We'd be seeing the same thing, but maybe attributing that as like just.
Well, what would we see it as? That's my sort of question, and that sort of, in a sense, comes back to this whole idea: is what is the difference between a galaxy and a star, and are there examples of galaxies that, I don't know, maybe they're not galaxies? So that's the end of part 1. There is a second part to this where we continue to discuss many more aspects of Arp's research. As always, be brave, be curious. The truth is waiting for us. Until next time.